Lab 5, Create Your Own Adventure by Shannon Schechter. The objectives for this lab was to analyze the projectile motion of a football ball being thrown and discuss the energy principles and concepts related to that motion. Create a model in Vital Python to show the object's motion, and using Newton's second law, predict the football's final position, velocity, and F-net parallel and perpendicular. When a soccer ball is kicked, the resulting motion of the ball is determined by Newton's laws of motion. From Newton's first law, we know that the moving ball will stay in motion in a straight line unless acted on by extended forces. If we know the initial velocity and position, and we can determine the forces, then we can predict the flight path using Newton's laws. So for this lab, the basic principles were Newton's first law, Newton's second law, and the energy principle, which we're going to calculate the total energy during this trajectory, and the kinetic energy and the potential energy. For Newton's second law, we have that the final velocity equals the initial velocity plus the net force divided by the mass and multiplied by the change in time. We have that the final position equals the initial position plus the average velocity times delta t. We know that the net force is going to be the sum of all the forces. In this case, the net force is going to be the drag force plus the force of gravity. The force of gravity is negative m times the constant d in the j direction, and the force of drag is going to be negative 0.5 times the drag coefficient times their density times the area's ball times the velocity squared. For the energy principle, we have that the kinetic energy is going to equal 1/2 times the ball's mass times the magnitude of the ball's velocity squared, and the gravitational energy is going to be the ball's mass times 9.8 times the ball's position in the y. Now I'm going to show you on Tracker the video. So we have the football ball being thrown, and we can see that on the x direction it is a straight line because the velocity in the x direction is going to be constant, but on the y direction it looks like a projectile motion, a parabola. And from this video on Tracker, first we got the initial position that is going to be 0.129 in the x direction and negative 2.11 e to the negative 2 in the y direction, and the initial velocity that is going to be 3.03 in the x direction and 7.6 in the y direction. Then we wrote the ball's mass, the constant g, and the constant necessary to know the force of the drag, the initial time, and the change in time. And we updated the ball's, here's the ball's momentum. And we have this while loop that ends at when the ball is at the floor. That is going to be the final time 1.43. And here we calculated the force of the gravitational force, the drag force, the net force, and the initial momentum and the final momentum, the ball's position, the new position, and the kinetic energy, the gravitational energy, and then the total energy that is going to be the sum of those two. And then when we run our model, we can see that here is the parabolic motion, just as the one we saw on Tracker. Then we have the red arrow that shows the momentum, the velocity, direction of the velocity, and the white arrow that is gonna show the force, the direction of the net force. And then over here we have the graph of the energies. So the green energy is gonna be the total energy. Then we have the red energy line that is going to be the kinetic energy, and the yellow energy line that is going to be the gravitational energy, and This graph makes sense because energy is lost during this trajectory because of the drag, and we can see that the kinetic energy is gonna start with a lot of velocity, then at the middle it's gonna have a low velocity, and at the end it will again have pretty high velocity. And then for the gravitational energy, it's gonna start really low because the distance from the floor is very small, the height, and then it's gonna start increasing, and when it goes down again to the floor, it's gonna decrease. So we can conclude in this lab that the computational model fit closely to the observed results. We can see over here, when we run again this, that the final velocity is going to be 1.93 in the x direction and negative 6.53 in the y direction. The final position is 3.56, and we had that in the tracker it was 3.67, and for the y direction we had that the final position here is negative 0.49, and in tracker we had that it was negative 0.38. And here we have that the magnitude of F perpendicular is going to be 1.21, and the magnitude of F parallel is going to be 2.72. And the results were pretty similar. It can be that they were different because of the center of mass. It was difficult to calculate at times in the video, and also because the drag coefficient was an approximation but not the exact drag coefficient. Thank you.